Okay, so this is a video editorial for the LeetCode Biweekly contest 179. The problems this time were like except I guess all of the ideas were fairly simple, but Q4 had some nice like sub optimizations you could do to make it run like even for the naive cases. But outside of that, the problems were straightforward for this contest. Like my performance was subpar because like I was trying to optimize something which like unnecessary optimizations in Q4, but regardless, I'll be discussing my solutions which I implemented during the contest in the order of the problems themselves, and after this I'll attach the live solve section where you can see my actual attempt during the contest. Q1 was like, I don't think it requires an explanation. Basically, given an array, we had to find the minimum absolute difference between two indices I and j such that the value at I was 1 and the value at j was 2. So since n is less than or equal to 100, you can easily just run a double for loop and solve this. Like even if this were like 1e5 or something, you could easily solve it by maintaining the indices where the values of where 1 and 2 occurred, and then minimize using that. So Q1 was straightforward. Q2 was decent, like it was decent for a Q2, I'd say. Basically, we are given n positions and an index pos and k. So basically, if I had to simplify the problem statement, basically we had to assign the directions of people such that, like if this is pos, we had to assign k people in this such that exactly k people are looking at pos, right? So if somebody is on the right side, then they should be facing this way, and if they're on the left side, they should be facing this way. And obviously the answer can be very large, so we return it 10 power 9 plus 7. My implementation during the contest was kind of like unnecessarily lengthy. There's a very simpler solution. What I did was, like if we assume pos to be at this index, for every position, like if we are at pos, then we have n minus 1 minus pos positions at its right? So for every position present here, we can run a loop for the number of people who will be facing this way. So if we know this, like if we have, let's say, x people facing this way, then on this side k minus x people should be facing this way, right? So here if we have r positions and we have to select any x people to choose look this way, that would be rcx, and similarly here it would be lc k minus x. And obviously we can like pre-compute the NCR values using the combinatorics techniques which are available. Like you can look for it like elsewhere. It's fairly straightforward. I don't think that requires an explanation. And for every x, we will multiply it by the k minus x to the combinatorics factor to get the answer. So this is what I did during the contest. Yeah, here basically I am running a loop on the number of people on the right side which will look at pos. So we can find the ways for this, and then this is k minus x, and this is the ways for left, and then we multiply that to the answer. But if you make an observation here, the code for this would be even shorter. Like instead of here, my solution was to the right side we are running a loop, right? But this loop is actually not required because what we have to do is select any k people, right, from this n minus 1. This is irrelevant. From this n minus 1, we have to select k people such that any k of them are looking at this. So the position is not relevant. So like if the person is on this side, they have to look here. If they're on this side, they have to look here. Instead of running a loop, we can just do this n minus 1 c k. This will give us a different number of people who are looking at this, and then at the end we multiply it by 2 because this person themselves can look at the both directions, right? So the code comes out to be even simpler. Basically it's just 2 into n minus 1 ck, and this will pass. Yeah. Q3 was an alright problem, I'd say. Basically what we had to do was like this pattern. I'm pretty sure you have seen this pattern like multiple times before. You are given an array of size m into n, and the constraint on m into n is less than or equal to 1e3. And here what we have to do is we can either move down or right, and we have to just find the minimum XOR value. Like if was the minimum sum value, then obviously this is a traditional problem like the minimum path sum. But the issue here is you can't just minimize the XOR values, right? XOR is not, the XOR operation is not defined over min. It doesn't work that way. You can't just do XOR, then take min and then do XOR again. The properties of the values will get lost. So instead of that, what we can do is we can see what all XOR, different XOR values we can reach. Since the problem state that the values are less than equal to 1023, right, which is 2 power 10 minus 1, so 10 bits. It's less than equal to this, so we can actually track, like at some I comma j, what all different values we can reach, like what all different values are reachable at some I comma j, and at the end at some n minus 1 comma m minus 1 we will have some, like some values will be not reachable, so that will be 0, and some values will be 1. So here in the state itself we can mark if this state was reachable or not, and at the end at n minus 1 comma minus 1 we would see the what is the lowest reachable state, and at the end we'll return that. So here this is what I did. This is like more of a DFS solution than a DP solution if you change this to visited. So basically I'm doing the XOR here, so that this is my current XOR. If I have already visited here, I don't do anything else. I mark this as visited and I go to right and left, right and down, and at the end I'm running this loop. Instead of this you can just make this dp n minus 1 m minus 1 x, then we return x, else we return x minus 1. This won't hit, putting this just in case. Yeah, this will pass this. Yeah, it's the same solution, it's not much difference. So this was Q3, like it was a more of it, like obviously since we are solving this using DFS, we can also like solve this using BFS as well, like, and that might be faster because it's iterative. And Q4 was an interesting problem. Basically we are given an array, digit sum of length n. Now we have, using this array we have to construct any array. We can construct any array such that the element itself can be between 0 to 5k. The array should be non-decreasing, which means like after the next element can be greater than equal to the previous element, it can't be less. And sum of digits at I should be equal to digit sum. So this is the, basically if sum at some I, if digit sum is x, that means like at some I, let's say digit sum is 4. Oh my bad. At some I digit sum is 4, that means we can place 22 here, 1 1 1 1, we can place this here, we can obviously place 40 here, since all of the sum of their digits is 4, right? So based on this, on the number of like values which can be placed at some digit sum, we have to find the number of valid arrays and obviously return it 10 power 9 plus 7. And this is just the definition of non-decreasing. And if you see here, the constraints are digit sum is less than equal to 50, n is less than equal to 1k, and this what do we say, the most interesting thing here is the value in the array has to be less than equal to 5k. Now we are given that digit sum is less than equal to 50. The maximum possible value here would be actually 31, since this can be 9, this can be 9, this can be 9, and this would be 4, right? So this is 27 plus 4, which is 31. So like even if digit sum were less than equal to 31, this problem would stay the same. So obviously like this, placing values at some array index and all is like giving DP intuition to me. So that is how I solved it. Basically my idea was, let's say at some DP I, also another thing here is to note here is, instead of one thing, like for problems like this where we have some composite function, right, here the function is the digit sum. So what you can do is, since the digit sum will stay the same regardless of the input, it depends on the number, so you can pre-compute these values and then you can check like what is the largest possible size, like basically how many numbers are possible for some digit sum, right? So I did this and I found out that approximately 365, like at max some value can have, some digit sum can have 365 numbers associated to them. So using this 365 and this 1000 gave me the idea for my DP solution. Basically what I'm doing is, let DP I x, I'm taking x as the variable, right? One sec. Yeah, let dp inx be the number of arrays starting from the suffix I, this is I, such that we are placing the xth element of I, like basically like assume we have some digit sum, let's say 4. So different values are possible here, right? So we'll have 4, then we'll have I guess 13, then we'll have 22, then 31, and so on, right? So like here x0 means 4, x1 means 13, x2 means 22, and so on. So I'm doing this because like in this way we can map a large range of values, which is 0 to 5k, to like at max 365. Like if you run this loop and find the maximum size, you'll see it's 365. So on when we are doing this our dp ix, obviously we have to ensure that the next element is greater than equal to it, right? So here what I was doing was I was finding the y such that the next element in the next array, like this is the sums array for 4, like if the sum of digits are 4, these are possible numbers. Let's say here it was 2 there, so what are the possible sums, the numbers which sum to this? We have 2, we have 1 1, we have 2 0, and so on, right? So let's say I was placing here x was 1, that means I am placing 13 here. So here I can only place elements that are greater than equal to 13, and in this array the elements that are greater than equal to 13 are from 20, right? We have 20, and then we have, let's say, 200 somewhere, and 101, and so on. So since I know my x, which means the number I'm placing here, I can binary search on this array to find the first number which I'll place, which will fulfill my condition, which is 20, right? So this will be the first number which will fulfill my condition, and after that all numbers will fulfill my condition, because if like 13 to 20 is our valid array, then 13 to 101 is also valid, and so on. That means this sort of structure can be we can, like, since it's a linear sum over dp, right, that means this can be easily optimized using a suffix sum, since we'll be summing from here, and so on. So this was my basic dp idea. So first I am finding the maximum possible, like the range, the maximum possible numbers, the value of x which can go. Then I am used to making this global dp arrays, because they can time you out if you don't do this. Obviously resetting it. Now yeah, this was an implementation. This is the suffix sum optimization. Basically sums the current digit sum and sizes the number of numbers which are associated with this digit sum. Now what I'm doing is, for every value, if x is less than if x is obviously greater than sg, let's say like for some number, where is print, what, let's say for some number 0, only 0 is the possible suffix sum, right? So for x equal to 0 this is defined, but for x equal to 1 this is not defined. So I'm just, in those cases I'm just setting dp to be 0. Else for defined cases, obviously for the base case dp would be 1, because only one array is possible. Else you can do this. This loop is basically, I am finding the next sum, which is the next digit sum, and then I'm binary searching to find the first value y, like the first index from which my sums will be valid, and then I'm doing the suffix sum thing. And at the end you sum all of the values here. Instead of this you could also do this. I guess this should also work, since we already have the sum stored in sfx suffix, right? Oops. This should also work. Yeah, we didn't run this loop. Yeah, I mean, yeah, whatever. And obviously here, since in dp we are at I, we are only dependent upon the I plus 1, we can easily optimize this to O of 1, O of n, O of 365 actually, space as well. That will like make this implementation even faster. So yeah, that was my idea for Q4. Alright, so like I'll attach my live solve section, which you can like look for references and like the techniques and whatnot. Alright, bye.